Good morning. Welcome to the lecture on biocontrol systems. Today we will be discussing on block diagram reduction technique. This technique is a very important in reducing a complicated closed loop system into a simple open loop system. It has multiple rules involved in it. We will go by simple rules and then extended version of the other rules. So as we said, block diagram reduction is a graphical algebraic technique to simplify the complex interconnected block diagrams of control systems into a single equivalent transfer function block. That is, an open loop system will be formed from a complicated closed loop system. And this conversion is being followed based on applying standard rules without altering the system behavior. The rules are: rule number one, if we have two cascade blocks, that is blocks in series, like G1 is one transfer function and G2 is the other transfer function. They are connected in series. The output of the first block is the input to the second block. In that case, we can represent this combination into its equivalent form like G1 into G2. So if you have two blocks in cascade, you can multiply them and form a single block. Similarly, rule number two is the combination of parallel blocks. Here parallel means G1, G2 are two blocks and they are connected in such a way that both blocks are getting the same input. In that case, we call them as parallel blocks. And depending upon the summing point sign, we will write the equivalent block as G1 plus G2 or G1 minus G2 depending upon the sign available there in the summing point. Here from the figure, we can say G1, G2 are the two transfer functions which are in parallel, and the equivalent form is you have added the two blocks G1 plus G2. The third rule is moving the takeoff point or the branch point ahead of the block. Let us say it is as shown in this figure, where A is the input signal passing through the block G. So the output of the block will be A into G. If we are taking the signal A through this branch point or the takeoff point, we will take the signal A. If we are trying to move this particular takeoff point ahead of the block G, then this can be represented as this. Without changing the character of the movement or the entire system, we can add a 1 by G in the takeoff points branch, so that whatever the signal which is being taken from this takeoff point A is available at this point. Rule number 4, moving the branch point or the takeoff point before the block. Let us say if you are trying to move this point here, and since you can see the branch point is having the signal AG taken out. So if I move this here, then the equivalent form of representation will be, I will add a block similar to that of the same block G, so that the output signal coming out of the branch point remains the same. Rule number 5, as the takeoff point is moved, we can also move the summing point ahead of the block and before the block. If I am having a summing point, let us say a, small a, if I am moving this summing point ahead of the block, then equivalent is as shown in the figure. So every time I have to add a block through which or ahead of which the summing point is being moved. So this signal B is passed through the same block G and A as similar to that of the same B. So I will get the same signal like A plus B into G as the output for the same equivalent form. Rule number 6. Moving the summing point before the block. Let us say if the summing point is located here and we are supposed to move the summing point after the block G, then obviously the equivalent form of the block diagram is by adding a block 1 by G in the flow of signal B, which does not alter the character of the output AG plus B, which is available in the same output of the equivalent form. Rule number 7, interchanging the summing point. We can combine these two summing points 1 and 2 and form, or we can interchange them like 2 will come here and 1 will be available here. And the character of the equivalent transformed form is not altering the output of the equivalent block. Similarly, if I have a combination of a summing point, like 3 signals are available in a single summing point, I can split this into 2 summing points like available figure here. A and B is added, then SE is being subtracted from that. You can see the equivalent form is not changing. Then again I can combine these summing points like the vice versa, the previous splitting summing points. If I have two summing points adjacent, I can combine these two summing points to form an equivalent form where the output does not vary in its equivalent form. Then the most important rule of block diagram reduction is elimination of a feedback loop. Let us assume that I have a forward path transfer function G and a feedback path transfer function H, and the feedback is a negative feedback. Then this closed loop system can be replaced with an equivalent form of open loop with G by 1 plus GH. And this can be explained through the signal which is coming out of the summing points, crossing out the block, combining them. The open loop, the closed loop system can be converted into an open loop system, which is represented like the transfer function C by R is equal to G by 1 plus GH. Similarly, if the loop is having a positive feedback, then a small change in the actual transfer function will be, instead of a plus sign available here, it is replaced with a minus sign. That is, C by R can be written as the forward path transfer function 1 minus the forward path into feedback path. This minus sign is the only change between the positive feedback and the negative feedback rule, which is being discussed in the previous. Thank you.